I think today we can say that it's economically attractive to waste material. Good evening, everybody. Very excited to be here and present to you our approach to the future of concrete construction. And it starts with digital rebar. Concrete can be cast into expressive forms. We can create amazing architectural spaces with very unique qualities, such as, for example, the Stadelhofen railway station just a few hundred meters from here. There is also potential beyond freeform architectural space making. We can actually create very material efficient structures as well in concrete. If we have the power to place material where it's needed, to place the reinforcement where it's needed, and the concrete where it's needed, we can actually make quite lightweight structures that use much less concrete than if you would, for example, create a solid rectangular structure. There is a problem, however, and I would like to tell you quickly about this problem. If you want to make, for example, a curved, single curved or doubly curved concrete wall, it is quite elegant in its final appearance. In the construction process, however, there are certain challenges. You actually have to start with a piece of formwork. For these kind of shapes, these are often custom-made elements. You then have to bend the reinforcement, place it within this formwork, add another piece of formwork before you can actually cast the concrete. So while you end up with a beautiful final shape, you also end up with two pieces of special formwork that you then often cannot reuse. So it actually ends up as waste. And this is a big problem. We have looked into this, and we have also realized that if you look into formwork emissions for these special shapes, this can be often more than the actual structure that you're building. So I think it's fair to say today there is no efficient way to create these kind of special forms. Which is a shame, because as architects, as structural engineers, we have the computational tools to create complex geometry. They can also be extremely material efficient. But if we then build them, if we bring them to the physical realm, we don't have the tools to actually do this in a cost-effective, material-effective manner. And of course, it's very labor-intensive as well. So this problem we were tackling when I was back at the university, and over the course of 10 years, we developed on a solution for this. And this solution, we decided to bring into a company and the product to the market. So what you see here is a doubly curved, fully reinforced steel concrete structure that follows regular building codes, but was built without special formwork. So there was zero formwork waste in the creation of this structure. So how do we do this? We combine formwork and reinforcement into a computational design and production process. We create a rebar cage using industrial robots. We weld a reinforcement wire, we place it, we build up a cage that can, of course, then act as a reinforcement within a concrete structure, but it also defines the actual geometry of the final structure. So we can fill them with a special process without conventional formwork. Let me show you how we do this. So we start with a reinforcement wire, conventional reinforcement wire from a coil, bend it with a bending machine, weld it together, the robot, and align it on a building platform. So we take 3D data from a client and directly generate reinforcement cages and all the necessary fabrication information to bring this into the physical world. What you see here is a process that we have developed specifically, the application of the horizontal reinforcement. So a robot places the rebar, welds it, and bends it in one continuous motion. And it can do this for straight cages or curved cages. The robot doesn't really care. So in this way, we can build up rebar cages very efficiently in a prefab setting using industrial robots. So you end up with a cage that you can then bring onto the construction site and assemble it into a larger structure. So from multiple smaller elements, you can do a larger structure. And this is an example of a project that we've built a bit more than a year ago, where we worked with local construction workers on a project in Germany. We brought these cages from Switzerland, put them together, and stabilized them with props before we actually concrete them. So what you see here is the Concreting, so we work with local concrete from a local concrete plant. Added additive, so it's a mixture that we have developed together with our partner company. And fill in this cage with conventional concrete pump without any formwork. We need to apply a layer of shotcrete cover to make the necessary cover, which can be left exposed as a shotcrete surface, or if you want to, can further treat it and make it a smooth surface, which we have done with this particular example. So with this method, we can now build complex, expressive, wall-like structures without the need for costly and material wasteful special formwork. We looked into the cost structure of producing this wall, and we're approximately 50% of the cost if you would use conventional doubly curved formwork. So we can save on the formwork. But how about saving on the actual concrete and steel within a structure? Today we know that there is huge potential to optimize on slabs. This is how it is done today in most cases. We have very efficient way of doing this in terms of speed and in terms of cost, but not so much in terms of material use. And we end up usually with these flat elements. I think today we can say that it's economically attractive to waste material. And we think there is large potential there to optimize this. So what we have done is a study with our colleagues at the Wald Galmarini engineering practice here in Zurich. We looked into a slab of an existing office building not far from here, and we're investigating if we could save on steel and concrete if we would use our technology for this. So we came up with a preliminary solution where we place the reinforcement where it's needed and make small adjustments in the geometry to reduce the amount of material needed. And a mesh that we would then produce like this would look something like this. So it's sort of a combination of a reinforcement cage for the slab that goes into the top of a mushroom column. And by these little changes, we have in first investigations show that we can save roughly 30% on steel and 40% on concrete by using this method. And we believe there's, besides the saving on material, there's also unique architectural qualities that come with it. This is a rendering that shows how such an office slab would look like. We think you don't need to hide your office ceiling anymore. And just last week, we made a first experiment to actually fill a mesh that is then placed horizontally. So what you see here is a very first example that we can also build into the horizontal. So to conclude, we use robotic and computational design to do tailor-made structures. A robot doesn't really care whether it's a one-off or we do it 100 times. We use it as a structural system, so we use normal concrete, we use conventional steel reinforcement, we use conventional calculation methods to define a structure. Very important, you can now do freeform structures that are without the usually occurring formwork waste. And as shown in the cost of this wall, this is a lot more cheaper than existing methods. So that's largely because of the formwork that is not needed anymore, but there's also massive potential in the automation of production of rebar cages, which is today mostly done manually. And lastly, as the slab showed, we can, besides the saving on the formwork, also save on the overall material in a final structure. This brings me to the end. Thank you very much. We are around 1 year old now as a company, so we're actually leaving next month the premises of the university. We have rented the factory hall around half an hour outside of Zurich to actually bring this into real projects. So we're looking for projects. If you'd like to collaborate with us, please reach out to me. Thank you very much.